Hello, this is Module 12. We're going to be talking about Earth science, and it starts on page 433. Go ahead and get your notebooks out to take notes, and here we go. So, geology. What is geology? It's the study of our planet Earth. It's the study of the physical structure, the composition, and the geological history, and the processes acting on it. We have the study of chemistry about the Earth and the study of physics about the Earth. So we have the geochemists that study the composition and the structure and the processes. And then we have the geophysicists that study gravity and magnetism and electrical methods and sound on our Earth. We can see microscopic worlds through microscopes. We can see far distant stars through telescopes, but we have very little information on the structure of the inner Earth. We can't look at it with our eyes. Scientists do know some information though. How do they get that information? Through seismic waves. So seismic waves are from earthquakes, and they're analyzed using seismographs to determine the speed of the waves or the energy lost during the travel and any direction changes. And with that, we're able to map the interior of the Earth. So the center of the Earth is about 4,000 miles deep. Scientists have drilled down to only about 8 miles to take readings and samples. Based on the information we've gathered so far, scientists have divided up the Earth into compositional layers, which is the chemical part, and mechanical layers, which is the physical part of our Earth. So there's different spheres of the Earth. They're called the geosphere, the hydrosphere, the atmosphere, and the biosphere. So the geosphere is what we are talking about. There's 3 compositional layers: the crust, the mantle, and the core. This picture here shows the different spheres of the Earth. And so we're looking at the geosphere here. It shows the upper mantle, the lower mantle, the outer core and the inner core, and the crust. And then here's another picture of the layers. So you have the upper mantle and the lower mantle, and then you have the outer core and the inner core, and then the crust is up here. Here's another picture in your book. It has the continental and oceanic crust, so the crust here, and then the mantle and the core. There's an outer and inner core, but we'll do that in a moment. And so just notice how thin the crust is compared to the mantle. The 5 mechanical layers that scientists have divided our Earth up into are the lithosphere, the asthenosphere, the mesosphere, and then the outer core and the inner core. I want you to pause the video and write those down. Write down the 3 compositional layers and the 5 mechanical layers. There's this picture in your book on page 436. If you don't own the student notebook, I want you to go ahead and draw it yourself and then label it and label the different parts. So go ahead and pause the video if you haven't done that, and go ahead and draw it and then label the different layers. I'm going to talk about the crust, and I want you to write down a few things that I say. Okay, you can write them in your notes. So the crust we can observe directly, obviously, the outermost layer of it. Most of it's made of silicates. The chemical compounds composed of silicon and oxygen. So silica equals silicon dioxide, and that's mostly sand and glass. Silicates also contain iron, calcium, or aluminum in a smaller amount, metals, but they're mostly sand and glass. The thickness of the crust varies depending on if there are mountains or deep oceans. So there's the continental crust, that's your mountains that you see. It can be really, really thick, right, if those mountains are tall. Or there's the oceanic crust that's under the ocean, and it goes pretty deep down, so then you're going to have a thinner layer of crust, and so it varies from 55 miles to 12 miles in thickness. The continental crust is mostly composed of granite, and the oceanic crust is mostly composed of silicate rocks like basalt, and it's very dense because of all the weight of the water pressing down on it. Now I'm going to talk about the mantle. If you don't have the notebook that you purchased, go ahead and draw this in your notes and label the different layers of the mantle. Okay, you can pause the video and do that. So there's this Croatian scientist, I'll try to say his name, Moharovacic, and he used the seismic waves and he studied the seismic waves, and he concluded that the Earth's interior had a border of discontinuity. So basically, where the seismic waves changed velocity, there was some sort of border. Okay, so this border is called the Moho discontinuity, and it's where the Earth's crust ends and the mantle begins. Okay, sorry, it's shaky. There's the Moho. You can see the crust, and then the mantle begins. Have we ever seen the mantle? Nope, we've never seen the mantle. But by analyzing how seismic waves travel through it, scientists think that the mantle is mostly silicate rocks, rich in iron and magnesium, and more dense because the deeper down, the more compact the material, and the deeper down, the higher the temperature. The mantle ranges from between 1,000 degrees Fahrenheit to 4,000 degrees Fahrenheit. The deeper down you go, the hotter it gets. And at the bottom of the mantle, the pressure is about 1.4 million times the pressure at Earth's surface. How many layers does the mantle have? The mantle has 3 layers. There's the lithosphere, the asthenosphere, and the mesosphere. So the lithosphere is the upper mantle, and it's solid, rigid rock. The asthenosphere is softer rock, so it's weaker. It's not completely solid. It's like taffy, but it's not like liquid. With an abrupt force, the rock will harden, and this is called soft plastic rock, and it may move in huge currents. Be taking notes on this as I am going through this. And then the mesosphere is stiffer rock, but it still does flow. It's just it flows really slowly. And this is called stiff plastic rock. So basically this kind of rock, it can flow sort of like a liquid, like a taffy, but if it has like a sudden pressure, it's going to solidify. So we've talked about the crust, we've talked about the mantle, now we're going to talk about the core. In 1914, a German geologist, Benno Gutenberg, found, through seismic wave information, another discontinuity below the mantle. This was called the Gutenberg discontinuity. This begins the Earth's core. The Earth's core is made of iron, not silicates. It has some nickel and some other lighter elements in it, but it's mostly iron. And it's liquid, not solid, because of the increased temperature, so the rock has melted with the increased temperature. In 1936, a Danish scientist, Inge Lehmann, he realized that the core actually has a solid inner region beyond the liquid. So it's now separated into what we know as the inner core and the outer core. And this is the Lehmann discontinuity, named after that man. So this is the boundary between these 2 layers, the outer liquid iron layer and the inner solid iron layer. Okay, so why is the middle not liquid if it's so hot down there? Well, the inner core is actually hotter than the outer core, but the incredible pressure explains the solid iron core. Even though high heat increases the kinetic energy and gets atoms to move apart and liquefy, the pressure here is what is causing that inner inner iron rock to go back to being a solid from liquid. This is known as pressure freezing. And the temperature down there is estimated to be 5,500 degrees Celsius, which is 10,000 degrees Fahrenheit. Okay, so let's review. What part of the Earth's core is liquid? It's not the inner core, it's the outer core. So you have the core, that little ball in the middle. You have the inner core and the outer core. The outer core is the liquid, and the inner core is actually the solid. The Moho discontinuity is between which 2 regions? Do you guys remember? The Moho separates the crust and the mantle. Okay, so we have the crust, and then we have the mantle beginning, and that's the Moho discontinuity. Where's the Lehmann discontinuity? So this is all the layers here, and this is the outer core, and this is the inner core, so this whole thing is the core, and the Lehmann discontinuity is in between the outer core and the inner core. Remember that our Earth has a magnetic field around it, and it's hypothesized to come from a large amount of electrical current flowing in the core, which generates the Earth's magnetic field. Remember, that's a hypothesis. We don't know for sure, we can't observe it. The magnetosphere is the area of the Earth's atmosphere influenced by the Earth's magnetic field. And then we have cosmic rays. Where do the cosmic rays come from? The cosmic rays come from our sun and also outside our solar system. They're mainly made of hydrogen nuclei, some are helium, but they're made of subatomic particles. They're basically made of protons that are stripped from their atoms. So it's a bunch of protons coming towards our Earth, and Earth's magnetic field deflects the majority of these particles. A stream of these dangerous particles is called the solar wind, and if Earth's magnetic field was too strong, it would cause deadly magnetic storms. But if the Earth's magnetic field was too weak, like you can see in this picture, Mars has a weak magnetosphere, and so it provides little protection. If our magnetic field around Earth was too weak, it wouldn't protect life from the cosmic rays. So it has to be just perfect to protect life. So the solar wind hits the magnetic shield, the magnetosphere, and they're deflected. But if the solar wind is really strong, these particles become electrified up in our upper atmosphere, and then they beautifully light up the sky into the far northern and far southern areas of the world. These electric lights are called auroras. The lights in the north are called the aurora borealis, and the south is aurora australis. So that's what I'm trying to show you here. The northern lights, aurora borealis. Quick review question. What causes the Earth's magnetic field? So it's the electrical flow in the core, the electrical current in the core of our Earth. That's the hypothesis. What major benefit do we get from the Earth's magnetic field? It blocks the cosmic rays from the sun, which is made of protons blasting at our Earth. So write some notes about that. You can pause the video and take some notes. Along with studying the interior of the Earth, geochemists and geophysicists also study the Earth's lithosphere. So the lithosphere is the rigid outer part of the Earth. It consists of the crust, but also a little bit of the upper mantle. Remember how big the mantle was in that one picture? So it's just a little bit of the upper mantle in the lithosphere, and it's composed of rocks and minerals. Now your book talks about sediment and soil. What's the difference? So sediment is weathered rock. It's small fragments of rock like gravel or sand or silt, mud or clay. And silt is just fine sand or clay carried by running water. You've probably seen it in streams. And the sediment develops as a result of movement. Okay? Soil is organic animal or plant material, decayed matter, and it's also inorganic grains of rock. But this soil develops in the absence of movement. So sediment is from movement and soil is from the absence of movement, and soil is more organic material and sediment is more rock, sand, mud, clay, that kind of thing. What are rocks made of? Rocks are made of broken pieces of crystals or other rocks. They can be made of shells, or rocks can be made of compressed pieces of plants. You guys remember what the three major groups of rocks are based on how they form? We have sedimentary rock, we have igneous rock, and we have metamorphic rock. So sedimentary rock is compressed sediment, so compressed sand or mud, and it's cemented together with minerals. This is going to be something like sandstone. If you grab a book about rocks, you'll be able to find pictures of sedimentary rocks. So we have limestone up here, which I'm kind of thinking that's what this is, but this is a sedimentary rock. Chalk, flint, sandstone. This could be sandstone. And then we have mudstone, shale, and I cannot pronounce that, conglomerate. Then we have igneous rock, and this forms from the cooling of magma the cooling of liquid rock. If it hardens underground, cools slowly, then large crystals can form. If it hardens at the Earth's surface, like with lava, it can cool quickly, and this forms small crystals or glass. So some examples here are basalt, we have granite, we have tuff, a rock formed from volcanic ash. We have obsidian. This is a really cool one. It looks like a black glass. It's volcanic glass that forms quickly and it has really sharp edges. This one's called gabbro, and over here is pumice. Then we have the metamorphic rock. This is igneous or sedimentary rocks that have been changed. Remember, metamorphosis means change. It's been changed from great pressure and great high temperatures. The minerals inside the rocks become unstable and they break down into other minerals. And so this would be like your quartz or your marble. And these can be different colors. I think this says quartzite, but quartz is usually like a white one, and marble often has different colors mixed in. This is a white marble. Okay, it says it right here, quartzite. This rock is made of quartz and is caused by the metamorphosis of sandstone. So that was rocks. Take notes on rocks. This is minerals. So what are minerals? Minerals are naturally occurring. They are not man-made. They're inorganic, so elements other than mainly just carbon and hydrogen. They are solids, and each has a unique chemical makeup. They have a crystalline structure, and they're the building blocks of rocks. So let's take granite, for example. Granite is made up of individual crystals of minerals. In this rock, there are two types of feldspar, quartz, and mica minerals. You're going to see mica when you go hiking in our area. It looks like a really thin, papery, shiny glass layer in the rocks that you'll find. It's pretty cool stuff. Feldspar is actually the most abundant mineral found at the Earth's surface, and then quartz is also one of the most abundant minerals. You'll find this when you're hiking all over the place. Mineralogists, they're geologists who study minerals, identify minerals based on these 8 properties. If you're my child, you might want to plug your ears. I'm going to sing a song. Crystal, color, streak and luster, density, hardness, fracture, and cleavage. So you can try to memorize those with a little song, but there's 8 of them. So let's go through each one. Crystal's easy. Some form cubic crystals. You have to look at it with a microscope to see the arrangement, right? And then there's 6-sided crystals, like with quartz. Some are 12-sided crystal gems. So the crystals can look different. Obviously, there's different colors of rocks. There's pyrite. That's the fool's gold right here. And it has a gold shiny color. Then there's silicon dioxide, and it's either clear or white. We have the streak. So geologists use a porcelain streak plate, and they scratch the plate, and there's different colors that show up on the plate, and a lot of times the color of the powder is different than the rock itself. The color of the powder after scratching may be different than the mineral of the rock itself. So there's different colors that way. You have the luster, which is either metallic or non-metallic. So you have pyrite that's pretty shiny, and then you have sulfur right here, pretty shiny, and then you have sulfur that's kind of the yellowy color, and you can see the difference in the metallic and the non-metallic. The non-metallic is described as earthy or silky or pearly or glassy. Then you have the hardness on page 443. Mohs hardness scale is used for this. So remember, atoms and minerals are held together by different strengths of bonds. And so you have talc is the softest as an example. That's a Mohs hardness of 1. Okay, that's right here. And then you have diamond, which is the hardest right here, and that's a 10 on the scale, and no other mineral can scratch diamonds. They're their hardest mineral that we know of on Earth. And then quartz is about a 7 right here. And it can be scratched by minerals with lower numbers on the scale. The scale can be used to identify rocks based on how the rocks scratch other rocks with known numbers on the scale. Geologists usually start by scratching glass, and if it can scratch glass, then they test by scratching it with other minerals harder than 5.5 to figure out where it is on the mineral hardness scale. And then we have fracture and cleavage, and they're kind of the same thing, but there's a little bit of difference. So I just drew pictures of what cleavage is. So the property of a mineral that allows it to break smoothly along internal planes when struck sharply with a hammer. So it's going to break along planes, straight, smooth planes. Like sheets of graphite can easily be pulled apart or cleaved apart from each other. And then fracture is the property of a mineral breaking in a somewhat random pattern with no smooth planar surfaces. So you just see kind of these cracks all over the rock. That's fracture as opposed to cleavage. Remember that rocks are dynamic. They're always changing over time. So next is the rock cycle on page 444. To understand this, I highly recommend you draw it out and kind of follow along the lines of how it goes sort of in a circle, in a cycle, right? And also I wanted to mention you should have been writing notes for each of those properties of different minerals. Okay, so the rock cycle. It's a process in which rocks continuously change from one type to another by forces within the earth and also forces at the earth's surface. Understanding the cycle can help geologists learn about the history of the area. Okay, so you're going to draw this in your notes and follow along. So let's just say we start with igneous rock. Okay, so the igneous rock is going to break down into sediment. And there's different processes that can cause this, right? Like weathering can cause the rock to break down into sediment. Okay, then it's carried by river or wind to the ocean, and then it's compressed by all of that water into sedimentary rock now. And then let's say it gets pushed deep underground and there's heat and pressure, and now it's metamorphic rock. Okay? And then let's say it gets heated. So it gets heated up and it turns into liquid rock, which is magma. And then it cools and now it hardens back into an igneous rock. So that's kind of the circle of it. But of course it can go the other way. The igneous rock might sink down and get melted into magma. Or we might have metamorphic rock turning into sediment. We might have igneous rock getting pressed down and heated and turned into metamorphic rock. Okay? So review questions. In what layers of the earth does the rock cycle occur? So this is occurring in the crust or the mantle, the outer part, right? How do rocks change chemically? Some elements are carried away and others are added by the fluids flowing through the rocks. Okay, so you're going to do the reading up to page 445. You can basically stop at where it switches to water. So don't go to the hydrosphere unless you want to. You can read ahead. But you're going to be doing 12.1 through 12.5, and just note that 12.5 is beyond those page numbers. It's on page 451, so just also do 12.5 because it has to do with the rock cycle that we just talked about. And then I highly recommend getting a rocks book and just looking through different types of rocks and trying to guess what type they are, what their names are, and how they formed. And it's just a good way to solidify what we just read. All right, thanks for watching. Here's a little bonus video if you want to watch it. You don't have to. So we have snowflake obsidian. This is a type of quartz That's a really fun one. Thomas is helping me find the rocks. He's 6. And so this is jasper. He's looking for a red jasper. That might be it. There might be something else too, though. There's green zebra jasper. And so you can see that quartz can be very different looking.
I think that's that.
Pumice is an igneous rock. Can you find pumice, Thomas? It's really lightweight because it has all these holes from how it's formed.
This one seems like it's plastic.
We have calcite, type of limestone. We have rose quartz. And here's hematite. This is a fun one, a form of iron oxide. It's pretty heavy, it's pretty dense. It also talks about its streak. It says, when you use that streak plate we talked about, it has a blood red colored streak, which is pretty surprising because it doesn't look red at all. And here's pyrite. So when we talk about the luster, this has a metallic luster. Looks like gold. Here's tiger's eye. It has a hardness of 7 on the Mohs scale, and it's also from the quartz family. Oops, it looks shiny. It's got a luster to it. This one is desert rose, and we often think of minerals forming crystals with angular sides and sharp points, but sometimes crystals can form in flat plates that stack up on each other. And you can have polished rocks that look a lot different from their raw form. That's all we wanted to show you. Thanks for watching.